signal non-digitized.
Right, you have something that looks like that, say, okay, with different amplitude because of different multiplication of these pulses. And when you pass these pulses, okay, through this low-pass filter, all the high-frequency components gets away. You get only the envelope back. Okay, you get y of t back. That's what essentially happens. Okay, because these pulses essentially has very broad bandwidth. Okay, and then this low-pass filter has a bandwidth that is very, very low. So the low-pass filter has a bandwidth of pi over capital T minus pi over capital T. This is my low-pass filter. And you see that in this low-pass filter, 2 pi over epsilon is much, much larger than pi over T. Okay, in the design of the low-pass filter. So it doesn't matter how narrow you make these pulses. Okay, you will not see the high-frequency components of these pulses as it passes through the low-pass filter. Okay? And it's immaterial as to how big this epsilon is, because it's so much higher than the frequency of the low-pass filter, and it doesn't matter. Okay? Yes?
When you look at Fourier transform over epsilon back to t over epsilon,
Right?
what if the 1 over epsilon cancel?
Is there a 1 over epsilon in the front?
No, like when you Fourier transform back to t over epsilon, you get t over epsilon 6.
Let me see. What is the Fourier transform of a rect function? Does anybody remember?
Tau 6.
The rect function. What is that?
Tau 6.
Tau 6, so you think that this would cancel?
Yeah.
Okay, so you think that a rect function of t over tau, Fourier transform to tau sin of omega tau, right? Omega tau over 2. So if this is the case, then this can cancel. This is not there then. Okay? This is not there. Then I don't have to worry about this. Okay? So it goes to 1, which means that, which is actually good. It goes to 1 instead of 1 over epsilon. So it means that it will not interfere with the working of the low-pass filter. These signals have some of these things, but it will not interfere with the working of the low-pass filter. Okay? Okay, maybe I can do it more carefully to show you that this actually doesn't matter that much. Okay, so what I'm actually doing here is actually doing something like that. So instead of working with this sequence, okay, I have shown you that this is correct. This Fourier transform to that. Okay, that is correct. But instead of working with this sequence in the real life, I work with an approximate version of this digitized signal that looks something like that. Okay, it's equal to Fn Pn t minus n tau. I work with this instead of that. Okay. This thing can be thought of as this thing convolving with PT, right? If I convolve with this with the above, okay, maybe I don't need to put a PN there. If I convolve this with that, I get the above. Can you see that? If I convolve the original impulse train with this pulse signal, which is not an ideal delta function, but an approximate version of the ideal delta function, okay, I will get back that, because this convolved with that will give me that. Delta T, NT, convolving with PT, gives me P of T minus NT. Okay? So now if I take the Fourier transform of this approximate rendition of this digitized signal, I will get Fd tilde of omega is equal to this original spectrum that I have found here, okay, multiplied by the spectrum of this, which is equal to, as I have derived over here, okay, the spectrum of omega epsilon over 2. That is what the spectrum of this approximate digitized signal is. Okay? So it just differs from the original spectrum by this factor over here. Now if I take this spectrum, which is Fd tilde omega, and pass it through the low pass filter, this is going to give me a very broad function, which is 1 almost everywhere, and the first zero crossing is 2 pi over epsilon. I'm going to multiply by this low pass filter. It looks like a box function, and the rect function equals 1 everywhere. So if I'm going to do that, then my y of omega will be equal to Fd omega sin of omega epsilon over 2 times my h of omega. My h of omega looks something like what I have drawn before. Okay, I don't know where it is now. Okay. But since this is so much broader than this one, I can just approximate this with 1, right? So this is just equal to Fd of omega times h of omega, which is equal to f of omega. Because Fd of omega is f of omega convolving with that, and then it just repeats itself periodically. And if I make sure that my sampling rate is high enough so that there's no overlap, there's no aliasing, then I get my original signal back. Okay, this is a more mathematical derivation of this system over here. Okay, is this clear? Is this clear? Georgie, is this clear? Okay, Georgie always gets it anyhow. Ria, what about you? Is this clear? She gets it too, so most of you get it too, I suppose. Okay? So the fact that what I'm trying to get at is that this pulse signal is going to do very little difference to the whole process, because the pulse signal contributes to this function, which is essentially just 1 everywhere. Okay? With a very far out zero crossing. So you can design pulse signals that are not exactly the other functions, and yet your system would work. And there's a very important theorem that says that the sampling rate is larger than 2 times the bandwidth of the signal, and this is called a Nyquist sampling theorem. And if this is satisfied, it implies no aliasing, no overlap. That's what it means in the Fourier space. And that is very important. So if you have a voice signal that is 20 kilohertz, if you want to sample this voice signal, which is 20 kilohertz, you must at least sample at 40 kilohertz. Okay, your sampling rate must at least be 40 kilohertz. And to convert it into the language of a signal processor is 2 points per cycle. Okay, you can think of a signal. If you have any signal, you essentially can write it as sum of Fourier harmonics of different frequencies. That's what Fourier theorem tells you and Fourier transform tells you. So what it says is that you take the highest frequency component that you can have, which is this one over here, and you have to make sure that your sampling rate captures the highest Fourier harmonics. That means that it has to be sampled at 2 points per cycle. So if you have a cycle, you need to sample it like this at least. Okay, if you have a cycle, you try to be clever and sample at 1 point per cycle, you get this. Okay, and if you sample something slower than that, you may get something like this. Okay, maybe with another point. And unless you're a magician, you cannot reconstruct the full cycle. But with this one, if you know that this is what you sample at the highest frequency, okay, then you can always reconstruct this thing. It's 2 points per cycle. Okay, what happens if you undersample? Say if you have a sinusoidal harmonic signal that looks like that, and then you sample at the rate that is lower. Okay, maybe maybe that's not a very good picture, but you sample only at this rate. Okay, then you get yourself confused. You might think that this belongs to a signal that looks like that, like a DC signal. Okay, you can't distinguish that signal from a DC signal, which means that so if you sample at a bad enough rate, you get this aliasing. Okay, some of the DC signal or low frequency signal will get into your band and get yourself confused. Okay, because of your sampling rate, and you cannot distinguish high frequency signals from low frequency signals. Okay, so much for today.